All right, here's the last part of 3.63. You might remember we're throwing this from shoulder height, trying to barely get it in the windowsill. We knew our initial and our final positions. We also went through the process of coming up with the equations that dealt with constant acceleration, acceleration in the x direction, and acceleration in the y direction, so 0 and minus g respectively. And we went through the process of eliminating equations we didn't use, and we said that for this phrase in the problem that says barely clears the windowsill sill, it implies that the velocity in the y direction is 0. So it made this term 0 and that term 0 right there. And I went off on a tangent and went in the wrong direction really during class. So let me see if I can get the rest of this problem worked out for you. So the reason I went off in the wrong direction is I was trying to get too fancy with it and trying to solve and substitute in to our equations for here I was trying to substitute in v naught times the cosine of theta, when I really didn't need to do all of that and make these more complicated. So these are the 4 equations left over from the 6. All I really needed to do is to remember that the theta that we're looking for is the inverse tangent of the y direction of the velocity over the x direction of the velocity, and that the magnitude that I was looking for is the square root of the v naught x and the v naught y. So v naught x squared plus v naught y squared. So if I could get those two things, then I could get the magnitude and direction. So I just decided to try to get those components and then use them. So this last equation right here, this right here was vy squared, but the final velocity was 0. So that means that if I'm looking for, if I'm looking for v naught y, then I can just move this to the other side and get a minus sign, and then I take the square root, so I get that it's the square root of minus 2ay y minus times y minus y naught. And I have all of this stuff. I know this from the statement of the problem. And so the minus signs cancel out here, and I get a positive meter square per second square root, so I get units here. So that's one of the things that I needed to know to get magnitude and direction for the initial velocity. Now, I realized then that if I wanted to find this, I needed to know how long it takes to get from my shoulder to the windowsill. So I'm going to try to use this one to get the time and then plug it in over here. So starting with this equation right here, I'm just going to follow my arrow all the way down until I get to right here. Yeah, I'll show you that in a minute. If I solve for time, I move this to the other side and I get negative v naught y over ay. And there it is. So the time required to get from my shoulder to the windowsill is the negative of this velocity right here, and I write that down in meters per second, and I divide by the acceleration due to gravity, negative 9.8 meters per second square. The units work out so that I get this time of flight, this time for projectile motion in seconds. Then I can go back to my original problem up here, our original equation, and if I solve for v naught x, it's just going to be distance divided by time. So v naught x, which is right here, is the x displacement from the first page of the problem divided by the time it takes to go from my shoulder to the windowsill, this right here. So I take that, put it here, distance divided by time, I get this, and this is my v naught x. And so now that I have v naught y and v naught x, I have the two components of my initial velocity. I can therefore take the inverse tangent to get the direction, and I can take the sum of the square root to find the magnitude of the initial velocity. All right, so that'll teach me a lesson here, not to substitute in what I was trying to do. I was trying to do this. I was saying v naught cosine theta, and I was complicating that more than I needed to. And I was doing the same thing for the y, v naught y over here. I was putting v naught times the sine of theta. That's making it more complicated. Really, all I need to realize is that I needed to figure out what the time of flight was, and then define the two components independently, and then use my magnitude and direction equations located here.